Okay, so your first real little test of this video. I'm curious, you'll have to tell me on Monday what you think of the videos. So, right before the bell rang, we had been looking at the app with the mean exam test scores. We looked at the power, how it was 68.3%, and we interpreted that as when we are looking at power, that means the alternative was true and we rejected the null hypothesis. So we did that correctly. That's the main idea of power, is that you reject the null hypothesis correctly. So we say, if the alternative is true, our test will correctly reject the null 68.3% of the time. So let me again show you in the picture. So if we look back at this app that we had looked at. So remember, in a significance test, we're always having to make our assumptions off of the top one, that the true proportion is equal to that 18.6, okay? But if this is actually the truth, remember we put in the truth as 21. If this is the actual truth, even though we're making our assumptions off of the top, this is where the samples are actually coming from. So most of the samples are going to be in the tallest portion of the sampling distribution because this is the actual population. Now, there's a chance that we could have gotten a sample in the white, and if we did get a sample in the white, that would lead us to fail to reject, which, according to this, would be a type 2 error. Remember that this section is a type 2 error, okay? But majority of the shaded region, this red region, is indeed where the tallest portion of the true sampling distribution is. So most likely, we're going to get a sample in this red region, which is why we say that this red region is 68.3% of the entire distribution, and that is our power. That's the probability of correctly rejecting the null hypothesis, because all of this section, we're going to reject the null hypothesis, and we should be, because the truth is 21. But there is a chance that we'd get a sample in the white area, and that would be a type 2 error. So the idea here is we want to have high power. The higher the power, the better. We want to reject the null hypothesis correctly, okay? So, sorry, I'm having a couple issues with the Smart Slate again, like usual. So this is what we want to investigate next, is like what type of power, or what types of things could we do to increase the power, because we want high power. So let's go back to the notes. And this is where it says, suppose we want to increase the power of the test. Remember that the power is the ability to to detect the alternative when it is in fact true, or in other words, the probability of rejecting the null correctly. So what is something we could do to the sample size? Well, I've talked about the sample size before. It's always the higher the sample size, the better. So right now we have a sample size of 8. Okay, let me erase kind of what's on here. Let's raise that to like 20, for instance. Okay? If we raise that to 20, take a look at what happens to our power. The power increased. That's because if you remember, what does a sample size do to a sampling distribution? The larger the sample size, the skinnier the sampling distribution. Remember that the sampling distribution, there's less variability with a higher sample size. So what happened is the centers actually didn't change. My center is still at 21 here, and my center is still at 18.6 here. But what happened is the tails got smaller. But because I increased my sample size, since the tails got smaller, that meant that's a smaller type 2 error and larger power. So let's go back up to the notes. What should we do to our sample size to increase power? We're going to increase the sample size, which will increase power. Okay, and I told you, increasing the sample size is always better in pretty much every situation. So the higher the sample size, the higher the power. So now it asks us, what should we do to our alpha level? Well, take a look at the picture. Let me go back to a sample size of 8, back what we were using. Okay, we're back to that power. Well, remember that this area right here, this orange area, that's your alpha level. Well, the alpha level sets where the bar moves. The bar moves when you move your alpha. So what do you think would happen to alpha to increase the power? Alpha needs to increase. Right now it's set at 5%, but if we increase it, the bar is going to move this way. But if the alpha goes to like 10%, it'll move the bar to here, which will change this red level. So let's see. As I increase alpha, right now it's at 5%, now it's at 10%, now it's at 20%. Okay, as I increase alpha, the power increases because remember alpha moves the bar. But here's an issue you want to think about. Yes, moving alpha will indeed increase the power, but remember alpha is the probability of a type 1 error. So while you are increasing power, which is a good thing, you're also increasing the probability of a type 1 error. So keep that in mind. So what should we do to the alpha level if we want to increase the power? We're going to increase alpha, which will increase power, but remember, and that does decrease beta, which is a good thing too. We want to decrease beta, but remember it does also increase the probability of a type 1 error. So actually I probably shouldn't say but decreases beta. I'll just say it does decrease beta, which is actually a good thing. Okay. What if we had a different alternative value? So I keep saying that we don't usually know the true value. We don't usually know what the true sampling distribution looks like. But right now we're saying, well, let's see what it looks like if the truth was 21. Well, let's increase that. What if the truth was even further away from the claim? What if the truth was 22? Well, what's going to happen is it's going to shift the center of this sampling distribution over. We actually did that in class with the other example. So let's see what happens. If I shift that over, look, the power again got bigger. And actually I should probably set this back to the 5% level. But the power is bigger if I went from size 21, like we were talking about before. If I changed it to even a higher truth, the power changes to 91.3. So another thing that increases power is this different alternative value. So an alternative hypothesis value that is farther from the null hypothesis will also increase the power of the test. So those are a couple things that increases the power. So lastly, we have this little chart, and the chart just basically wraps up what we were saying here. Our goal for alpha, remember alpha is the probability of a type 1 error. So our goal for alpha is to make as small as possible because we don't want to make a type 1 error. Our goal for beta is also to make as small as possible. Okay, because again, we don't want to make a type 2 error. But power, we want to make that as large as possible because power is correctly rejecting the null, which is what we want to see. Okay, but again, as you can see up here, depending on what you do to the different levels, will change alpha, beta, power, and things like that. So let's see the relationship. What happens if we increase alpha? Well, I'm going to put a sad face on there because increasing alpha is increasing the probability of a type 1 error. But if we increase alpha, what that's going to do, again, I'm having mouse issues. Let me try this one more time. Really, it's going to do this when I'm almost done. Sorry, you guys are waiting on me. Okay, here we go. Hopefully I can get through this without any more issues. If we increase alpha, which is a sad thing because that's increasing the probability of a type 1 error, it will decrease beta. But that's a good thing because it decreases a type 2 error. And what does it do to power? It increases power, which is also a good thing. So notice that as alpha goes up, beta goes down, and power goes up. So alpha and power actually always do the same thing. Power is always the opposite, because remember, power and beta, let me try that again. Alpha and power always do the same thing. Beta is always the opposite, because beta and power have that 1 minus relationship. Okay? So lastly here, I don't know what just happened to that. My mouse is really driving me nuts. There it goes. I don't know. We're just going to keep going. If we decrease, okay, this is driving me nuts. I'm going to pause this real quick. Okay, you probably didn't even realize that I paused it, but I did pause it to try to fix this. So as we decrease alpha, that's a good thing because it decreases the probability of a type 1 error. It's going to increase our beta, which is a probability of a type 2 error. That's not necessarily a good thing. And it will decrease power, which is not a good thing. So there is this weird relationship here. We always want to make this as small as possible. We always want to make this as small as possible. We always want to make this as large as possible. But as you can see, alpha and power change the same way, always. Increase, decrease, decrease. Beta is always opposite. So my question is there a way to decrease alpha and decrease beta while also increasing power? There's only one thing we can do, and that is to increase the sample size. Okay? So this ended up being a 12-minute video, and I got kind of mixed up here in the middle because of the mouse issues. I didn't have those issues with the other videos. So hopefully this at least wraps it up a little bit for you. Give me your feedback on Monday. Enjoy your weekend. Okay, bye-bye.